Hi guys, today we're going to talk about behavior trees and control barrier functions. And most of the material is taken from the paper to the right, which is joint work with Özer Özkaraman. And my name is Petter Ögren. So why would you want to combine behavior trees and control barrier functions, or CBFs as we will be calling them? Well, they are complementary in many senses. Behavior trees do hard switching between policies or controllers. First, one controller is executed, then another is executed. Whereas control barrier functions do soft merging of objectives. They're executing one controller while taking another objective into account. We're going to see what this means. And furthermore, convergence proofs of behavior trees require not violating earlier subgoals. And control barrier functions do exactly this. They provide guarantees for not violating earlier subgoals in terms of staying in certain sets of the state space. And we also need a way to handle tradeoffs when some subgoals have to be sacrificed to preserve others. So this is kind of a result of the combination of control barrier functions and behavior trees that we will see. So this combination gives safety guarantees in the sense of classical control barrier function safety guarantees. We can guarantee we're not going into the unsafe set, whatever that is. But we can also use them for this kind of hierarchy of different sets that we want to be in and sets we don't want to be in, and so on. So this combination can be seen as a generalization of the standard use of control barrier functions, if you will. So the key idea of control barrier functions is illustrated by this nice picture. We have a car over here, we have a speed limit, and this is a dock, so at some point there's water that we don't want to drive into. So the idea is that the closer you are to the edge over here, the more careful you have to be, which is a fairly well-known concept, right? So you need to drive slow when you drive close to the edge, basically. So we can imagine this being implemented by a set of speed limits that have reduced speed as you come closer to the edge and the water. But more importantly, slower speeds are important when moving towards the edge. So imagine going this way, you would like to go slower, but if you turn around and head in the other direction, maybe even fairly close, you can kind of speed up because you're going right here, and then it's not so dangerous anymore. So you can imagine that if we have positive velocity or positive speed to the right and negative speed to the left, the speed limit over here with a large margin would be plus 90 to minus 90. Whereas if we get closer, 60 plus 60 to minus 60. Whereas if we get closer, it would be plus 60 to minus 40. And then the negative, this limit on the negative values here decreases to 0, negative being moving leftwards here. And here you're not allowed to move with any speed leftwards, because then you're going to plop into the water. So again, this is the key principle. The closer you are to the edge, the more careful you have to be. So let's see if we can kind of generalize this natural concept of the speed limits, or formalize, if you will. So let's we have a coordinate system here with the variable h being the distance from the edge, and then h being positive is a nice thing. So h is distance to the edge. If we differentiate h with respect to time, dh dt, we have the speed. So again, positive going right and negative going left. H larger than 0 is the acceptable or safe set. That's when you're here. If it's smaller than 0, you're basically here, which is a bad thing in most circumstances, at least if you're sitting in a car. And then the speed limit, as shown here, it kind of decreases when h becomes smaller. We can actually formulate it as in terms of this equation. So this would be the speed again. So the speed has to be larger than minus h. So this is, here it's minus 30, minus 20, minus 10. So maybe this is 30 meters, 20 meters, 10 meters. So the closer you get, or some other unit. So the closer you get to the edge, the closer the speed limit comes to 0. Yes. So minus h, obviously, you can draw the curve like this, minus h, it's not rocket science. And then the allowed speeds are larger than that. So this is the set of allowed speeds going obviously up above this point. So if you're at the brink here, the allowed speed, it has to be positive between 0 and 60. But if you have a margin of 10 here, you can go 10, whatever the velocity unit is in the negative, but you can go as fast as you like in the positive, or up to 60. Okay, so this obviously guarantees safety. If your speed decreases like this linearly when you approach the edge here, in the worst case we're going to have equality here, and you might notice that if we do have equality here, we're going to approach the edge here exponentially. So as time tends to, if we have equality here, we keep going this way, but as time tends to infinity, the position is going to tend towards the edge here, but we're never going to drop off. But that's the worst case. So can we generalize this? I mean, this principle is kind of natural to humans, and here we have an equation that we kind of pulled up out of our sleeves, more or less, given this example. But can we generalize this? And yes, we can, and that's what control barrier functions are. So here comes some math. So the key idea behind control barrier functions is to specify a barrier function h. Now it's not just the distance to the edge, but some barrier function, so that the safe set C is characterized by all the x's that are evaluated positive. Again, think of the distance to the edge, but it could be some other function. And then we have a continuous dynamical system, x dot equals some fc of x and u. We have a control here. So if we choose controls in some set, where this is a set, so this resembles our speed limit thingy, but it's a bit different. If we choose the controls satisfying this inequality, and this alpha is a class k function, we're not going to go into details there, but it's basically a function that increases with increasing values, we're guaranteed to stay in the safe set. So this generalizes what we saw earlier. This is our speed limits in the docs here, and we can see that this actually generalizes. This is a special case of this guy. So if we have alpha y equals y, so alpha is just the identity function here, so we have minus h here. So if we just flip this, we have minus h here, we have minus h there. And you can note that this expression, dh dx, f of c here is actually, fc here is dynamic, so that's x dot, the time derivative of x. So this is dh dx dx dt, which simplifies to dh dt, which is over here. So as you can see, this is a special case of the more general function here, where we allow a general dynamics, whereas in this case we just assume that we could set the velocity of our car, which is fairly reasonable but not totally true. I mean, you can't just, if you're driving fast, you can't just set your velocity to 0 and then it happens instantly. You can set it on the cruise control, but it's going to take some seconds before it actually happens. So, but the key point is control barrier functions guarantees us to stay in a safe set as long as we choose controls inside satisfying this inequality. And then this set might be empty, so you need to kind of design your control barrier function wisely, and it's actually a relation to something called Lyapunov, control Lyapunov functions up here, but we're not going to get into those details now. So we talked about control barrier functions. What about behavior trees? For behavior trees, we need set invariants for them to converge. And what do we mean by that? We want, so this is a generic behavior tree. So we want the execution here, jumping from one action to another action to another action. We want it to kind of progress in the right, to the right next action, and avoid the wrong ones, whatever the design is here. Right and wrong might be different things, but we want some kind of doing something first, doing something else, and then doing something, and then we're all happy. We don't want the kind of our actions to fail and end up having to redo stuff or things like that. So we're going to formalize these kind of fluffy arguments. So we do not want to violate achieved subgoals. As the following examples, we want to avoid moving into the unsafe area. If we started getting into the safe area and then we want to do something else, we don't want to move back into the unsafe area. So imagine this is a child here. We are not allowed to be too close to the child when it plays. So if the robot starts in here, we're moving out here, but then we want to get to the goal point, but then we can't just go straight for the goal point, because then we're going to move into the unsafe area again. So we want to kind of move around it. We want to avoid running out of batteries if safe is defined in terms of having enough battery. We want to arrive on time if we need to be somewhere at the given time. We want to stay inside communication range. Maybe that's a requirement. We get inside communication range. We don't want to violate that sub-goal by somehow moving out of that range if it's deemed important to be inside. We want to avoid giving the same fork to two guests. So what kind of example is this? Well, imagine you have two dudes here at the restaurant and they should each have a fork. Then we can't just give a fork to the first one and then say, okay, he's happy. This guy needs a fork. Okay, let's just, there's a fork over here. I'm going to give it to him, because that would violate the sub-goal of this guy being happy. And then, oh, this guy needs a fork, and then we give it back, and then everyone is going to be really pissed. So we want to keep some set invariant. That is the key commonality of all these examples here. And controlled barrier functions can do that, as we just saw, as long as we pick controls in these sets and compute the sets. So let's look at some of these examples from earlier videos, just to make sure that you notice that this is indeed something we so we had this video, 4 common bugs in backward chain behavior trees. So if you haven't watched that video, this is going to be a bit confusing perhaps, but basically what we need for an action move to object, for instance, it needs to achieve its post condition in finite time. So it needs to move to object, needs to get the robot near the object, but it also needs to not violate key previously achieved subgoals, such as this is the in safe. First we make sure we're in the safe area, and then we try to get the object here. We can't try to move to the object by getting into the safe area. We're not allowed to do that. And we should not violate conditions needed for later actions, such as free path to goal exists. We cannot violate that condition while doing this, then we're not going to be happy overall. And we cannot invoke previously failed subtrees. This is a bit complex, so just you need to check that video to see the details. But the take-home message is we need to not violate earlier achieved subgoals and stay in some sets for this, the whole BT to achieve the overall goals and kind of achieve its mission, basically. And this is another video of analyzing behavior trees as discontinuous dynamical systems. Then we looked at this in terms of a state space here, and we noticed that if we only have transitions as shown in the arrows, so if you're somewhere in this omega-1 set, then we're guaranteed to end up in omega-2, and here we're guaranteed to either end up in the success region or in omega-8, and here we're guaranteed to go to the success region. and so on, according to these arrows. If we can guarantee this, and then all this transition happening in some finite time, upper bounded by something, then we know we're going to end up here. That's the only thing that can happen. We're leaving omega 2 in finite time, and we're going either here or there. Then all executions leads to success, which is a good thing. But how can we guarantee this, that omega 2 only goes here or there? Basically, we need to make sure it doesn't go into the omega 1 region, and it doesn't go into the failure region. So we need to make sure that this set over here is invariant, that we don't move out of it in these directions. So again, invariant sets. So can we keep all sets invariant in general? Well, sometimes the general answer is no. Sometimes you have to do trade-offs, because this in sets to be invariant, it depends on your mission, right? And sometimes you're giving an impossible mission, just like Tom Cruise. He gets impossible missions all the time, and money for those missions, I guess. Okay, so imagine you have this robot, you have some Wi-Fi over here, you want to stay inside the Wi-Fi range here, you have a charger over here, so you want to stay in range of this charger. The thing is, when time goes and your battery depletes, the range you have to be in order to make it back there before you run out of battery decreases. Like this. So you have to be inside this green bubble and that green bubble, and at some point you can't be in both. So you can't make everyone happy. Either you need to stay in Wi-Fi range and go out of battery, or you have to leave the Wi-Fi range to recharge. You can't do both. And if you have some child here that you're not allowed to go closer than some safety distance here, it becomes even more complex, right? And if you have obstacles, even more complex. So in general, you can't make everyone happy. You can't expect to make everyone happy all the time. So sometimes trade-offs are needed, and then we need to make those in a rational way, which is in most cases corresponds to violating the least important subgoal. So someone needs to decide if staying inside connectivity or getting recharge is more important, and then you keep whatever is most important, and then you have to sacrifice the other subgoal. And if there's a child here, maybe you should just stay here and run out of battery instead of going close. Or you're allowed to move super slow close to the child. I don't know. But trade-offs are needed. So in order to look at these sets here, we're going to do set intersections of control sets. So we need some way to illustrate control sets, some kind of notation here. So how do we illustrate a set of controls? So we imagine that your control of this robot is velocity. You're allowed to control velocity in the plane here, which is basically vectors. So the control set is a set of vectors. And then for a set of vectors, we can use some kind of pie chart to illustrate those sets. So in this case, you want to stay inside the Wi-Fi connectivity here. If we go right, we're going to move outside of it, so that's not okay. Going left is okay. Going slightly up and slightly down and down to the left is also okay. So basically, this set of velocities are okay. This set is okay, so kind of going upwards, going downwards, and going to the left is okay. Going to the right is not okay, because then we're going to leave this area. And then we're going to illustrate this kind of, so this is just not 5 vectors, but this is an infinite set of vectors pointing in here. So we're going to illustrate this by this kind of pie chart thingy, all this infinite set of vectors lying here. Then obviously you can either go fast to the left or you can go slow to the left, so there's a shorter vector here as well, but we're going to illustrate it by a pie chart, all of those options. Yes. So let's see an example where we actually look at these equations then. So we have the robot over here. We want to be inside network connectivity, and we don't want to be inside the red blob here, getting too close to the child. So as we had, the assumption is that each condition in our behavior tree can be formulated in terms of a controlled barrier function, with the set basically being the x's that result in positive values for this h, which is a barrier function itself. And then in order to do this trade-off, we're going to formulate 3 sets, ki, kj bar, and kk hat. We're basically, and then when you have the sets, we're going to choose a control that is close to some k that is nice for whatever we're trying to do now, but we're only allowed to choose use from this k hat guy in order to try to satisfy the previously achieved subgoals. So this k without the bar or the hat is basically preserving one CI. This is the standard controlled barrier function setup here that we saw in earlier slides. So we have a bunch of things we want to achieve or preserve. The green one and the red one staying out of the red, staying inside the green. So the green is 1, say that's C1, and the red might be C2 then. So then we can find control sets, kind of like this. For the green one, it's okay to go left here, not right. And then another set here for the red one, it's okay to go upwards. It's not okay to go downwards to the right. And then we take the intersection of these sets. So it's basically okay to go upwards, and it's okay to go left. It's not okay to go downwards. And then there's going to be some allowed controls over here. That is the intersection. And then if that intersection is empty, this is where k hat comes in. So k hat is some kj for a possibly smaller number where we sacrifice the least important subgoals, such that kj needs to be non-empty, and either it's the same that we ideally want, or the one that has a larger number is empty. So it's kind of the biggest index here that is non-empty. So that's how we sacrifice subgoals, by finding the biggest index that is non-empty. If the index we want is indeed empty, otherwise we pick the one j equals k here. So this preserves all the CIs achieved so far. This preserves many of the CIs, but it's never empty, and this can be empty. So let's just look at this. What happens in this example with the intersection here. So with respect to the green thingy here, as we just saw, it's okay to go slightly downwards, it's okay to go slightly upwards, it's okay to go left. So this is allowed velocities from the green perspective. From the red perspective, this is allowed velocities. It's okay to go right, it's okay to go left, it's okay to go up, but it's not okay to go downwards right here. So then we intersect these sets here. Intersecting these sets basically means taking this guy and putting it on top of this guy, and then the intersection is this set over here, and that's basically what we see in these arrows up here. So these arrows are all the arrows that lie inside this blue pie chart. So it's okay to go upwards, slightly to the left, it's okay to go left, slightly downwards, and everything in between, but not going right and not going down. So that's how you find, and obviously this intersection, if we're not lucky, it can be empty. So this guy can be empty, and therefore we remove sets here until the intersection is non-empty, and then we get this k hat. So let's look at the problem. So the robot is over here. It tries to go to the recharger over here, while losing battery all the time. So the green blob here, as you know, it's going to shrink, but it starts having the robot inside it. But then everything would be green. So I illustrate it like this here, and we have some children over here, or areas that we should not enter, and some of them have just a totally forbidden area, but some have kind of an inner area that is not allowed at all, and then you would like to have an extra safety margin. So maybe this is a younger child, I don't know, or more, maybe this guy is sitting and reading and this guy is running around, so you would like some extra margin over here. So you want to avoid the unsafe area. That's your first priority, and that's the deep red areas here. You want to get to the charger before the battery runs out, and you want to, if possible, avoid the extended unsafe areas, but getting to the not running out of battery is more important than that. So that's your mission. So ideally you want to do like this, but maybe if you're low on battery, it would be okay to do like this. It's at least that wouldn't run out of batteries. So let's look at the behavior tree for addressing this mission here. First priority, avoid unsafe areas. Then we check if you're in the safe area. If not, we move to the safe area. Second priority, get to charger before battery runs out. So we check if the battery margin is okay. That's basically if we're inside the green area, that's going to shrink. If we're inside the green area, we're good to go. Otherwise, we need to go to the charger straight away, but hopefully respecting this guy. If the margin is okay, we check if the extra margin is okay. If so, if not, we move out of the extra margin. If the extra margin is okay, we're good to go. And then if everything is good, we just go to the charger. So this is our BT, and then we're going to execute this. We're going to use control barrier function to take this already achieved subgoals into account, not just going straight blindly to the charger, but try to preserve these guys while going to the charger using control barrier functions. So the execution is going to end up looking like this. This is the trajectory here. So let's see what happens. So the charger sits over here, and the robot starts over there. So first, everything is dandy. We're in the safe area. We have a good battery margin. We're also in the extra outside the light blue areas here, corresponding to the light red one. So over there. And then this guy is running, so this is our running symbol for the day. So then this happens, kind of, it tries to go to the charger over here, but it also makes sure that we satisfy these constraints going kind of outside these thingies here. And this is what the equation looked like, just to remind us. Then at this point, something happens. It's actually so now battery margin is starting to get crucial here because of these detours. So actually preserving all these extra safety margin, battery margin, and in safe area becomes impossible. The intersection over here becomes empty. So then we need to sacrifice some of the subgoals in order to get a non-empty intersection. So we, instead of going for K3 here, where we intersect K1, K2, and K3, we basically have to look at just the intersection of K1 and K2, and then that's going to be non-empty, not taking the extra safety margin into account. So that's why we start moving in here. So now we're trying to go to the charger without respecting the extra safety margin. So we move into here, and at that point, obviously the extra safety margin is no longer guaranteed, and we're going to violate it. So this returns false, and we're going to start running achieve extra safety margin. But that doesn't mean we're going to go out here, because extra safety margin now has to guarantee these two. So since we're actually at the limit of the battery margin being okay, we're going to continue going towards the charger, even though we would like to move out here. The control set that we're allowed to pick from is going to force us to go this way. And then we come to this place where actually we can no longer achieve both of these anymore, because this is the most important guy, and it's going to force us to go down. And since the battery margin was really on the verge here, we need to sacrifice that as well. So we do that, and then we're running go to charger here while satisfying in safe area root, and that is going to bring us all the way to the goal. So even though we're out here, we're still kind of violated our margin here. And that's why it makes sense to put your desired margin. If you know you might violate the margin like this, maybe you don't want to put your desired margin at 0%. Maybe your desired margin when going to the charger is 5% or something. So you actually have some extra time to if you need to violate this, to not go into the unsafe area. So let's look at some naive designs and what they might lead to. First, imagine we have no battery check. We remove this part of the subtree. Just worrying about in safe area and extra safety margin, okay. Then we just go to charger, respecting those conditions like this, and then at some point we're going to run out of battery. So that's not that good. In another case, without using control barrier functions, but having the same design, we would start over here, we'd remove this. In the start, everything is nice and dandy. All these earlier subgoals are achieved. We're gonna go to charger, but now we're not taking control barrier functions into account. So we're gonna go straight for the charger until we violate the extra safety margin. And then we're gonna be running achieve extra safety margin, just moving out of that area. And then at some point, this is gonna be satisfied. We're going to go to charger again, going back into the area. So we're going to end up basically going back and forth here, switching between achieve extra safety margin and go to charger here. So this design, without taking the earlier achieved subgoals into account in any way, is really not a good idea. But using controlled barrier functions, as we suggested, it works fairly well. So using BT control barrier functions to do planning. So looking at this, you might say, oh, well, this looks kind of shitty. Why aren't we just doing this? This is much better. Just heading straight into the obstacle here, or the unsafe area, doesn't seem very smart. Well, the reason is that classically, well, this looks better. So classically, as a standard control barrier function approach is local. So this is what the control looks like. You pick a U inside of this allowed set that is as close as possible to some desired control K of X. So if this K of X is go to charger, you're going to have something that goes straight to the charger unless you really need to do something else not to violate these constraints. So it is kind of a local by design. However, and that might make sense. Imagine this is kind of a crowd. There's lots of kids running around here. You can't really plan for moving through a crowd. You need to, when you get close to someone, you need to take a detour. But it could also be the case that you do have you have knowledge of everything here, and all the kids are static, they're reading or whatever. Then planning does make sense, and then you can do that. So you just use a path planner, whatever you prefer, perhaps an RRT, and you find a path that satisfies all your BT control barrier function constraints. So this is an example of RRT, if you like RRT, or you can do RRT star as well. But RRT, usually just you look at the free space and the obstacles here, then you just add this control barrier functions in safe area, battery margin okay, extra safety margin okay. Add those as obstacles in your path planner. Then you get a path plan that goes all the way, or as long as you like. If you want to do some kind of receding horizon control approach, you get a path, and then you just use that path as your K up here instead of the kind of the naive local greedy one. And then you try to choose controls that are close to your planned path, but in the safe set. So if everything is static, moving along the path is going to be in the safe set. But if the children starts to move here, you're going to do detours like this from the plan. but still having the safety guarantees. So we're going to look at another example. We're going to do patrolling with 3 vehicles. So the objectives in this example is to avoid collisions, do not run out of battery. So basically we're going to start with 3 vehicles up here, down here. We want to do some kind of patrolling in the area here. There's going to be some obstacles that we need to avoid. Do not run out of battery. So the charger is going to sit here at the start. So at some point we need to go back and recharge. We want to stay within comms range, communications range when patrolling. So this is the Wi-Fi symbol indicates their communication range, which is these small green circles. And this large or the brown circles that are going to be shrinking is actually the battery range. So right now the battery range of this guy is here, and the battery range of these guys are way outside, because this is kind of, these guys are fully charged and this has only, I don't know, 40% or 30% or something. And then we want to go through the waypoints, which is these purple guys, to the end over here. So the BT, the control barrier function BT, achieving this looks like this. Avoiding collisions is priority 1, so we're checking if we're safe from collisions. If not, we avoid them. Priority 2 is do not run out of battery, so can we reach a charger with a margin, just like the example right before. And here we have some extra details here on the subtree achieving that. We check if the charger is visible. If so, we dock. If not, we do a search pattern. So you can have as much detail here as you want, obviously. This is still kind of a sub-goal, and if you achieve it, this guy is going to take it into account. And then priority 3, stay with comms range when patrolling. Connected to another agent, then you do rendezvous. So note that going out of battery is more, not running out of battery is more important. So if the group moves like it's going to be doing here, and one runs out of battery, he's going to go back and not worry about the comms range. And the other 2 are in range of each other, so they're good to go. But at some point, one is going to be good to go, and the other 2 goes back to recharge. Then he's going to follow them, because even though he's good on battery, he's going to stay within comms range, because it's not allowed to do patrolling alone. And then you go through the waypoints as your 4th priority. So this is basically what it looks like when it's running. So this guy is going to run out of battery first. This is his range. So when the range is at the charger, he goes back to recharge. The other guys continue. Then he goes back to rendezvous. He's going to rendezvous at the waypoint, so now he aims for this waypoint. These guys keep patrolling, and this is their battery ranges, so soon they're going to be recharging, but first they kind of continue patrolling here, and now they go back to recharge. He needs to be in comms range, so he follows them. They recharge very fastly, and now they're good to go, all 3 of them. They stay in comms range, doing the waypoints, and then head up to the end of the mission here. But now actually this guy who had low battery to begin with, now this guy needs to go back and recharge. They continue patrolling. He recharges and then goes back to finish the mission. So that's how it might look. And again, this is having kind of the standard local control barrier function setup. So you might have realized that this guy, instead of going up here and then back to recharge, he should just stay and recharge immediately. But that involves planning, and we didn't do planning in this example, but it's perfectly possible if you want to. So just a final note on safety guarantees. With this setup, we can note that this K1 set, which guarantees safety or guarantees invariance of our first set, this K hat guy here, over here, is always going to be, so it's an intersection of sets, so it's always going to be inside K1. So the controls we use all the time are always going to be inside K1. So that means we're always guaranteed to satisfy the first priority condition. Whatever happens down here, we talked a lot about trade-offs and contradicting objectives and achieved sub-goals, and you have to sacrifice some. Maybe you have to sacrifice being connected, maybe you have to sacrifice recharging and so on. But the priority one goal is always priority one, and it's always guaranteed. So you can see this. So the standard control barrier function design, usually you have one safety thing that you guarantee with the control barrier function, and then you do something else. So you can see that as kind of a special case of the approach we decided, looked upon here, where you have multiple goals and you try to achieve all of them, but that's not always possible, and then you do trade-offs and so on. Yes, so just looking back at the motivation for combining behavior trees and control barrier functions, they are complementary. Behavior trees do hard switching, and sometimes doing that naively is going to get you into problems. And then the combination makes sense because you can use control barrier function to do soft merging, making sure that whatever controller you're executing now also takes earlier achieved sub-goals into account. So execute one controller while taking other objectives into account. We also noted that the convergence proofs, either kind of in the backchain design or in this general operating region version, they require not violating earlier sub-goals, and control barrier functions do exactly this. So that's why it's a good match, and we can also handle trade-offs doing the intersection here, but checking that the intersection needs to be non-empty, so possibly dropping sub-goals when you cannot achieve all of them, dropping the least important ones. So the combination of behavior trees and control barrier function, it gives you safety guarantees in terms of your priority one objectives, but it tries to achieve the other ones if possible. And by noting this, we can see this as a generalization of the standard use of control barrier functions. Thank you for watching, and if you want to get more details, you check out this paper, co-authored by Özür Karaman. And if you want to know more about control barrier functions, you might want to check out this early paper, one of the first papers on control barrier functions. It was called Behavior Control Lyapunov Functions at the time, from 2006. Or if you want to look at the more recent papers on control barrier functions, theory and application, I can recommend this paper. And in general, more knowledge about behavior trees can be found in this book that is available for free on arXiv. Thank you for watching.